I'm going to be explaining the Gauss-Jordan elimination process and reduced row echelon form to someone as instructed. I have specifically selected you, the viewer, as my victim. The Gauss-Jordan method can be used to find reduced row echelon form and thus solve systems of linear equations. If the following are present, it is in reduced row echelon form. So, 1. All rows that are solely zeros are at the bottom of the matrix. 2. For all non-zero rows, the first non-zero entry is 1 and is called the leading one. 3. In two consecutive rows, non-zero, the first one in the top row is to the left of the first one in the bottom row. 4. Every column with a leading one has a 0 in every position above and below the leading one. So let's walk through an example. I'll be using my own created problem from a previous part of the final project to demonstrate. So this is my created problem. So solve for the following system of linear equations using Gauss-Jordan elimination. So negative 2x plus z equals negative 4, 3x plus 2y plus z equals 36, and 4x plus 2y plus z equals negative 28. Okay, so these over here are what are referred to as rows. So when I say, row 1, row 2, etc., that's what I'm referring to. And each row is numbered in accordance to its succession from the top. So row 1, row 2, row 3. And then if there were more, then you would go beyond that. Okay, so let's start. So first, you want to take the given equation here, or the given system of equations here, and put it into row echelon form. So what you want to do is you want to take the coefficients of each variable and put them into the matrix, and then over here you put the products and such. So the reason that there's a 0 here is because the coefficient for y on the first one is 0. So that 0 is necessary though, otherwise it won't be solved correctly. So the goal is to eventually produce reduced row echelon form. So in order to do that, the first thing that was done, and there are various orders in which you can solve this, but this is the way that I found best for this specific example. So the first thing I did was multiply row 1 by negative 1/2. So essentially, that would cause negative 2 to be multiplied by negative 1/2, which would produce 1. So there's our first one. So the first step in row echelon form, and then you multiply every single number in the row. So then that gives you 0, negative 1/2, and 2. And then the second step is um, you take row 2 and then you subtract 3 times row 1, and then that becomes the new row 2. So um, another thing that's important is that you can't multiply rows together, nor can you divide them together, but you can add and subtract them together, and you can scale them. So that's what I'm doing here with the negative 3. I'm scaling row 1 so that the scale matches row 2, and we're able to eliminate the first value here. So because it's 3 and negative 3, that would be 0, and then the rest is as follows. So uh, 2, and then 5 over 2, and then 30. So then after that, you do row 3 minus 4 row 1 equal R3. And so 4 minus 4 is 0, and then the rest 2, 3, negative 34. And at this point, um, there are certain rows that you can start uh, reducing in order to achieve leading one. So after this, you go here and you would do half row 2 in order to divide 2 by 2, which is just 1, and then the rest is as follows. And then here, row 3 minus 2 times row 2 is row 3. So put row 3 here, and then row 2 times negative 2, um, negative 2 times 1, negative 2, negative 2 times 5 over 4, negative 10 over 4, etc. And then you simply find the difference or sum, if you will, depending on how you look at it. And so then you have you're starting to see the pattern. So there's a 1 here, and then eventually there will be a 1 there, so that all of the coefficients for each variable will be 1. Because remember, from up here, these numbers here are all coefficients of the variable. So when they equal 1, all that's saying is that this variable is itself equal to 1. So theoretically, if you were to plug it in to check, you would be able to find that these are all correct if multiplied out and added together. Okay, so 2 times row 3 is row 3, so simply 2 times 1 over 2 is 1, so then you get the 1 there. And then down here, you get half row 3 plus row 1, and that will eliminate. Now we're working from the inside. So now we're trying to make it so that all of the numbers that are not leading ones are equal to 0. So right here, this negative 1/2 has to be taken out. So in order to do that, that's why row 3 was multiplied by 1/2 again. And then so there is no longer a 1/2 there. And then almost there. So we got up here, so negative 5 over 4 times row 3 plus row 2 in order to eliminate that 5 over 4 there. So then that becomes 0. And then so this is reduced row echelon form. There's all leading ones, and every other number is a 0 above and below. Quick correction. The answer down here were written incorrectly. So let's continue. So as follows, this is going to be x because it is the first coefficient and its value equals 1, and therefore it is x's identity. And then so x, y, z. So we got x equals negative 62, y equals 175, and z equals negative 128. And that is how you solve row echelon form. And this is my example. Through my research, I've also discovered that Gauss-Jordan elimination has real-world applications as well. Essentially, anything that requires an input and an output model can possibly at some point use Gauss-Jordan elimination. In chemistry, the quantity of reactants, for example, can be determined through Gauss-Jordan elimination. The ratio of each chemical can be systematically discovered via such a process. It can also help economists make predictions about the future of the economy. Given a specific input or decision, it can help predict the economic outcome. Assuming that the values in the equations quantify aspects of a game such as moves, Gauss-Jordan elimination can also be utilized to find the optimal game strategies. Game theorists may find themselves doing such math in order to discover the most efficient ways of playing. These are just a few examples that I was able to find. Thank you for watching my presentation and taking the opportunity to learn what Gauss-Jordan elimination is, how it works, and how it can be used.